Assalamualaikum and welcome back. Now we will talk on the second topic, which is the um, non-causal associations of epidemiological study. So talk about the objective, the task, the delivery, and then we go to the introduction, and then we talk about confounder, exposure, and outcome, exceptions to this, theoretical and graphical aids to frame confounding, and how to assess the presence of confounding. Then we talk about mediation, confounding and suppression effect, evidences, and types of confounding. So the non-causal association epidemiological study. Alright, so what we are going to do is, number one, we want to understand what is non-causal association, which is basically confounding lah. Then we would like to be able to identify confounding problems or issues in studies. And number three, we would like to know how we can prevent and control confounding in studies. So the contents largely came from this book, chapter 5, Epidemiology Beyond the Basics by Szklo and Nieto. This is our textbook. Okay, alright. Then if you got time, then please read chapter 14 and 15 in the Epidemiology book, 5th edition by Leon Gordis. Okay, this one should be 4th edition, right? And then you can read this paper, Causal Knowledge as Prerequisite for Confounding Evaluation and Application to Birth Defects. Not an easy paper. If you got time, please read. If you got time also, please read this paper, Equivalence of the Mediation, Confounding and Suppression Effect. Okay, and what we expect from you is that you will be able to use your understanding and your critical thinking to understand what does it mean by confounding or non-causal association, right? In a simulated scenario, right? Right. So introduction, okay? Confounding refers to a situation which a non-causal association. There is association, but it is non-causal, okay? One does not affect the other one. Alright. So this association exists between a given exposure and outcome observed as a result of the influence of a third variable. The third variable is designated as the confounding variable or a confounder. So variable number 1, variable number 2, right? And this is variable number 3. Okay, so more likely to occur in observational study. than in experimental study, right? Because experimental study use randomization. Okay, randomization reduces the likelihood that the groups under comparison differ, right? With regard to both known and unknown confounding variables. How we can explain confounding? We can use counterfactual model, which actually tell us that attributions of causation to a particular exposure is based on the concept that the risk of the outcome observed among individual exposed would have been different in the same individual had the exposure been absent. So because the latter group by definition unobservable or counterfactual, epidemiologists are forced instead to use different group. Okay, so the unexposed, so we got this exposed and the unexposed, okay, as a counter factual. And then because you got exposed and unexposed, you can do comparison, right? So and the essence of the analysis rests on this assumption. This is very important assumptions that separate unexposed group is comparable to exposed individual if they had not been exposed. It means that these two groups must be very, very, very similar except for the risk factor. And confounding is said to be present if this assumption is not correct. The assumption that both groups are comparable. Okay. So this assumption is not correct if the risk in the unexposed is not the same as that in the unobserved counterfactual exposed group had its member not been exposed. You have to use your imagination to understand this, right? It is also important to emphasize that any conclusion regarding confounding or mediating effects, okay, two different things, one confounding, two mediating effects, based on previous consideration should be also based on solid theoretical understanding, right? It is not a statistical issues. It is more to theoretical understanding of the mechanism underlying the association under investigation. So that's why it is, a solid and explicit conceptual models are very, very important. Okay. So understanding what the conceptual framework or models between variable 1, okay, variable 2 and variable 3 and how they are related is very important. Okay. And on top of that, additional methodological tools can help you to process these concepts. All right. Confounder, exposure and outcome. Traditionally, confounder is defined by 3 criteria. Okay. Number 1, it must have, the confounder must have association with the outcome. Okay, confounder with outcome. Right, sorry, it should be that way. Okay, confounder should be the risk factor for the outcome. Confounder cause outcome, right? Second, confounder must be associated with the exposure, right? And last, confounder must not be in the causal path. Okay, so you can have exposure, then confounder, then outcome. You can't have this. Okay, confounder cannot be in the causal path, right? So first, confounding variable is causally associated with the outcome. Okay, confounder and outcome, arrow like that, right? One single-headed arrow. And non-causally or causally associated with the exposure, right? You can have this one, or you can have that one with the exposure, but not an intermediate variable in the causal pathway between exposure and outcome. So exposure there, outcome there, you can't have confounder here. Okay, it is not like that, right? Page 178. I'm not sure, third edition or fourth edition, this one. So yep, so this is confounder. You see one single-headed arrow to the outcome, and there is two possibility, either associated with or cause exposure. One single-headed arrow, double-headed arrow there, and the exposure is, you know, might or might not cause the outcome, right? So again, this is a unidirectional arrow, and this a bidirectional arrow. Very important. There is a situations where a third variable is known as a mediator. So this is independent variable, or the exposure variable, and this is your outcome. But this way, but for this model, there is the arrow goes from exposure to this third variable. Okay, this third variable. So this mediator is in the causal pathway. So it is not a confounder, because confounder cannot be in the causal pathway, right? So so this is not confounder. This is known as mediator. So what we have from this model is indirect effect, direct effect, and the total effect, which is the sum of effect of this and this and this, right? Although the general rule is that confounding variable must be causally associated with the outcome, sometimes random statistical associations also result in confounding. All right. Variable treated as confounders are occasionally surrogates. Okay, surrogates. Okay, they become the representative of the true confounding. For example, educational level is a surrogate for socio-economic status construct. Gender treated as confounder, but basically the true confounding variable are the sexual or hormonal difference, which can be used as markers for attitudes, behaviors, and exposure that are associated with gender due to contextual or cultural circumstances. Theoretical and graphical aids to frame confounding, to improve our understanding of the confounding. Theoretical construct is important, and you can use graphical aids to improve your understanding. Again, the issues are the conceptual definition, because this is not a statistical issue, this is a theoretical issues, alright. And then the directionality, which it is not easy to say which causes which, right? Whether it is a single-headed arrow or double-headed arrow, because there are lots of variables. So we need level of understanding, hypothetical, to describe or hypothesize the underlying pathophysiology, right? That is basically represent the relationship between the suspected risk factors, confounder, and outcome. So if you make your model more explicit, the analytical approach will also be more straightforward. It means that if you understand your model very well, all the variables in the model, then your analysis will be easier. If you don't understand the functions of the variables, then it will make your life miserable. Okay. One way of looking at the relationship is to use an analytical aid, which is known as directed acyclic graph, or DAG, right? So also known as a causal diagram. This is an example of directed acyclic graphs. Where you have aspirin, platelet aggregation, coronary artery disease, right? So DAG here shows the alternative hypothesis on the relationship between aspirin and risk of coronary artery disease. So this is exposure, this is outcome. But because the arrow goes from aspirin to platelet aggregation, so this is not a confounder, right? This is mediated, right? Mediated by platelet aggregation. So basically platelet aggregation acts as a collider. And actually it is confounded by unmeasured genetic variant. Okay, this one that is not measured in the model. Alright, you can refer to this paper. So this DAG illustrates hypothesis that aspirin reduces the risk of coronary artery disease through a decrease in platelet aggregation. Okay. Based on this hypothesis, in order to evaluate the mediating effect of platelet function and possibility of additional mechanism, this can be assessed by equation 5.1 in the book, right? Try and look at equation 5.1. Another model is that DAG figure 5.6b, the other one. There is unidentified factor, a genetic variant, hypothesized to be causally related to the suspected intermediate variable and the outcome. In this situation, the relationship between the intermediate variable and the outcome is confounded by the genetic variant. Okay, so you got two causal pathways. Okay, two causal pathways. One is aspirin platelet aggregation, CHD. The other one is genetic platelet aggregation, CHD, and both converge or collide at the suspected intermediary platelet, which is the platelet aggregation. So platelet aggregation is said to be a collider. So it is demonstrated that under certain assumption, the unknown genetic variant, the association between genetic variant and platelet aggregation, if you adjust for the latter, may introduce bias, right? That is, it may result in the spurious estimate of the association between aspirin and CHD. So you have this aspirin, and you have this platelet, and you have this CHD. So because there is genetic variant here, a confounder for CHD, if you include platelet in your model, the association between aspirin and CHD will be less, spurious, okay, because you add platelet inside here, right? So that's what happens when you include platelet in the model, right? Another example is you got periodontal disease, which leads to tooth loss. Tooth loss leads to diet problem. Diet problem leads to coronary heart disease. In B, periodontal disease lead to tooth loss, but there is also problem of socioeconomic status lead to tooth loss and also coronary artery disease. And tooth loss leads to problems in diet, and problem in diet will lead to coronary artery disease. So this shows alternative hypothesis, relationship between periodontal disease and risk of coronary artery disease. So this is basically what we are interested to look at, right? In A, baseline periodontal disease and tooth loss are assumed to be caused by past periodontal disease. So though its relationship to diet, tooth loss is hypothesized to be an intermediary variable. Okay. In B, socioeconomic status is hypothesized to be a confounder of the association between tooth loss and CHD. So because of this, sorry, total loss is a collider, and unmeasured variable are represented with faded font. So this is the unmeasured variable. So to understand DEX, directionality of the arrow is critical, and it is not, again, it is not a problem of statistics. It is the problem of theoretical understanding and conceptual model for the analysis.